In this video, we're going to talk about linear correlation coefficient. So numerical summaries of bivariate data should be used in addition to graphs to determine any relation that exists between two variables. We'll look at what is called the linear correlation coefficient. And this measures the strength and direction of a linear relation between two quantitative variables. So I've given the formula below, and I've represented that, for instance, x bar is a sample mean. S of x is the sample standard deviation of the x variable or the explanatory variable, so on and so forth. Now, when we take a look at the correlation coefficient, we'll round it to 3 decimal places. And we will use the calculator to determine this correlation coefficient, and we will not do this by hand. Okay? So note, linear correlation coefficient has no unit of measurement. So when describing the relation between variables, think STD. No, get your mind out of the gutter. The STD I'm referring to is strength, type, and direction. So for each of these, I'm going to write out some keywords on what you can use for these. So let's start with strength. Could be strong, could be moderate, could be weak, or none. So the type would be either linear, nonlinear, but might have a pattern, or no pattern at all. And the direction will either be positive or negative. So this is our strength, type, and direction that we'll be using to determine the relation between two quantitative variables. Okay, some properties of linear correlation coefficient. Number 1, R can be in between -1 and 1, meaning it could be -1 and it could be +1, or anything in between. So if R is equal to 1, then a perfect, strong, positive linear relation or association exists between the two variables. The closer R is to 1, then the stronger the evidence of a positive association between the two variables. If R is -1, then there's a perfect, strong, negative linear relation that exists between the two variables. The closer R is to -1, then the stronger the evidence of a negative association or relation between the two variables. If R is close to 0, then there is little or no evidence exists of a linear relation between the two variables. This does not mean that there is a relation, it just means it's not linear. So we've done some examples here below with this. Again, the top left, that's positive, perfect positive linear relation, R is equal to 1. We've got one where the correlation coefficient is approximately 9/10, then 4/10, and then the top right is a perfect negative linear relation, R is equal to -1, and we have R is approximately equal to -9/10, R is equal to -4/10. There is no relation. And the very final one is not a linear relation, but you can tell it looks like it's an upside-down parabola. Okay, remember, think STD, strength, type, and direction. So I'm going to write below that if you have certain particular numbers, what wording that you can use for this. So let me start with 1 or -1. This would be a perfect, strong, positive linear relation or association. The next one I'm going to take a look at might be this inequality. 6/10 is less than or equal to R, which is less than 1, or -1 is less than R, which is less than or equal to -6/10. Here's the wording I would use for this. I might write strong, positive linear relation. Okay, suppose R is in between these values. Then this might be what I would write for the relation here. So moderate, positive, linear relation. All right, suppose you have this now. And this is what I would write here. a weak positive linear relation. And if r is equal to 0, then I would write this. Remember, it's not saying it doesn't have a relation, it's just not going to be linear. So, how do you know the correlation between two variables is strong enough for you to conclude that a linear relation exists between them? Although rigorous tests can answer this question, for now we will be content with the simple comparison test. So, testing for a linear relation. Number 1, determine the absolute value of the correlation coefficient. Number 2, find the critical value in Table 2 from Appendix A for the given sample size. The table is shown below. Number 3, if the absolute value of the correlation coefficient is greater than the critical value, we say a possible linear relation exists between the two variables. Otherwise, no linear relation exists. Okay, so let's take a look at an example with this. So determine whether a linear relation exists between time to drill 5 feet and depth at which the drilling begins. See example 1. Comment on the type of relation that appears to exist between the time to drill 5 feet and the depth at which drilling begins. So let's go back and take a look at this example very quickly now. So here is the drilling example that we're going to take a look at. Now remember, when I put this into the calculator, the depth at which the drilling begins, that's going to be L1, that's the explanatory variable. And the time to drill 5 feet, that's going to be L2, or the response variable. So let's put these values into the calculator now. Now, before we do that, we need to make sure we do something with our calculator. We need to have what's called the diagnostic on. So how do you do that? Hit second and the number 0. That should bring a catalog, and we're going to go all the way down to D, which is going to be diagnostic on. So you keep hitting the down arrow like I'm doing here. So diagnostic on. Once this arrow is next to diagnostic on, hit enter again, and we're done. Keep in mind, you only have to do this one time. Okay, now let's put the data values in the calculator. So hit Stat and Edit. Right. So I've already typed in the data values for L1 and L2, so make sure you do that. Once you've done that, hit Stat, highlight Calc, and we're going to go down to number 4, which is lin reg AX plus B. Hit Enter. X list is L1, the Y list is L2. There should be nothing for the frequency list, so I cleared that out. Go down and highlight Calculate, and hit Enter. Now, the value we're looking at is the R. That's the linear correlation coefficient. So I'm going to round this to 3 decimal places, which is going to be 0.773. So let's put that in the calculator now. Okay, so I'm going to write out on the paper here, that's 0.773. So I need to check, so I'll do this on the side, the absolute value of negative 0.773 needs to be greater than the critical value. Well, if you go back and take a look, we know that that data set has 12 values. Since it has 12 data values, that's the decimal that we're going to use. So it needs to be greater than this. Well, clearly this is greater than this. So there seems to be some sort of linear relation that's going on here. Okay, so I'm going to write this out now. Since the absolute value of negative 0.773 is greater than 0.576, the correlation coefficient suggests that there is a strong positive linear relation between the time to drill 5 feet and the depth at which drilling begins. So again, we're talking about an STD for this. The strength, the type, and the direction is being explained here. Again, make sure you talk about the two things that we're comparing. In this case, the time to drill 5 feet and the depth at which drilling begins. Also, keep in mind, it's only suggesting. It may or may not. We will be doing future tests to verify or disprove this accordingly.